Section 3.2 is logarithmic functions and their graphs. Logarithms are inversely related to exponential graphs. Here I have a note. Recall from chapter 1 that if a function is one-to-one, meaning that it passes the horizontal line test, such as a graph like this. In other words, a horizontal line will not touch this graph at more than one point anywhere. So if a graph passes the horizontal line test, then it has an inverse. Well, the graphs that we were looking at in the previous section, the exponential graphs, do in fact pass the vertical line test. We saw graphs that look something like this. Those pass vertical line tests. So these have inverses. Well, as it turns out, the inverse of an exponential graph is a logarithmic function. So first thing I want to do here is define a logarithm with you guys. Here's the definition, taken pretty much directly right out of the book. Sorry about that. So if we write something log, and this is how we read this. I put down here in blue how we read this. This is pronounced log base A of x equals y. What that means is that a, whatever number that may be, raised to the power of y will give you x. So that's the definition. Now up here are some points to note that the x value has to be greater than 0. That'll become a factor later on. We'll show some problems with that. The a value must be greater than 0. So we're not going to be taking negative numbers, or 0 for that matter, and raising them to powers, because that would not fit into what we're doing here. And a cannot equal 1 also, because if it was, and I took 1 to a power, it would always equal 1, so we're not interested in that. So here's a few examples for us to try to evaluate. See what these equal. Now again, we're using the definition here that log base a of x equals y means a to this power equals that number. So with that in mind, and I encourage you to pause anywhere along the line once you feel like you've kind of got what I'm saying here. Sometimes you'll see this like this. Sometimes it'll say solve for x. Okay, so well this means 10 to what power equals 100? 10 to the x power equals 100. Well, hopefully it jumps out at you that x would have to equal 2. So I could say that log base 10 of 100 equals 2. Again, pause anytime you want here and resume and see what the solutions are. Here, 10 to what power is equal to 1,000? 10 to the third power. Number 3, 10 to a power is equal to 1. Well, if you remember, anything to the 0 power is equal to 1. So that's equal to 0. Here's some different ones. 10 to a power is equal to 1 over 100. Well, make a little note up here. If I say 10 to a power is equal to 100, 1 over 100, sorry about that. Hopefully what jumps out at you is negative exponents. 10 to the negative 2 would mean 1 over 10 to the positive 2, which does equal 1 over 100. So this is a negative 2. And so hopefully you see that this is going to equal negative 3, because this is 10 to the negative third power, which means 1 over 10 to the positive third power, which will equal 1 over 1,000. And the last one here, hopefully you got it, is 1. 10 to the first power is equal to 10. Now a little note here, a logarithm is an exponent. After doing these, and after you get the hang of it, hopefully you see that log base a of x is the exponent. This is equal to the exponent to which a must be raised in order to get x. That's exactly what we said here. For instance, going back up, here 10 must be raised to the second power in order to equal 100. So that's exactly what I'm saying there. Here's a few more for you to try. Again, I encourage you pause the video, work these out, resume the video, and see what we get. Log base 2 of 8, this is going to equal 3 because 2 to the third power is equal to 8. 2 times 2 is 4, times 2 is 8. Here, 3 to a power is equal to 9. That's going to equal 2 because 3 squared equals 9. This one's also going to be 3 here. Let me circle our answers so it doesn't get too busy. This is 3 because 5 to the third power, 5 times 5 is 25, times 5 is 125. The more familiar you get with the numbers, the quicker you'll be at getting these. Here, 2 to a power equals 32, that is going to equal 5, because 2 to the fifth power is equal to 32. We'll do that one together. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 equals 32. This one here, a little bit differently. I got 16 to some power is going to equal 4. How could that be possible? How can a number be raised to a power and make it smaller? It'll happen when you have a fractional exponent. So if I say, let's extend this down here. If I say 16 to the 1/2 power, that's the same thing as the square root of 16, which equals 4. So over here, 8 to a power equals 2. Again, how can that happen? Well, if I take the cube root of 8, I get 2, so the cube root of 8 can be thought of as 8 to the 1/3 power. So this is equal to 1/3. Now, base 10, log with the base down here of 10, we call these common logarithms. They're so common that they put a button on your calculator for it. And in fact, let me just point that button out here for you. Here it is. So if you are ever doing a base 10 problem, you press this button, your calculator will automatically do a base 10. So here we already saw that log base 10 of 100, what is it equal to? It's equal to 2, because 10 squared equals 100. So let me show you that. We would just type in 100. We don't have to type in the base. What did I do here? Let's clear this, try it again. I did something wrong. Log of 100 is 2. Let me go down here to log of 1,000. 10 to what power equals 1,000? That should equal 3. So I chose a number here. Put the answer here. Now that works great. We can do it in our head as long as the numbers are nice powers of this number. 10 squared is 100, 10 cubed is 1,000. If you're familiar with these numbers, you'll get that. But 10 jumps to 500. So 10 squared is 100, 10 cubed is 1,000. So I would expect log base 10 of 500 to be something in between 2 and 3. So the nice thing is we have at our fingertips here a calculator that can figure this out for us. So there we have it. Let's call that the 2.7 power approximately. Now we can do weird things like this over here. These are certainly not anything that you would do in your head. Log base 10 of 4.1. Well, we rely on the calculator. That's the beauty of having it. So I type in log 4.1. I get 0.61, we'll call it. That's the power that I would have to take 10 to in order to get 4.1 as an answer. So about 0.61, I'm sorry. Now you can work along here and see that when I type in log of 1/4, and I make sure I put that 1/4 in a parentheses, I get negative 0.60, so negative 0.6. And when I do log base 10 of negative 3, this one I want to show actually. So log of negative 3, what 10 to what power equals negative 3? No power. You can't take 10 to a power and get a negative answer. So that's going to be undefined. Okay. Here's some properties of logarithms, some things that I would, and they are on page 189, but let's go through these. What is the log base a of 1 equal to? In other words, what power would you have to raise a to in order to get 1 as your answer? Well, anything to the 0 power equals 1. So log base a of 1 equals 0 because a to the 0 power will equal 1. Log base a of a, what will this equal? This will equal 1 because a, the base, to the first power is equal to a. Here we have a little bit of a more confusing one. A to a power equals a to the x. Well, it's equal to x. A to the x equals a to the x, basically is what that's saying there. Now this one here, a to a power equals something. Well, let's look first at what this part up here is. Log base a of x. I'll change colors here to show this off to the side. This means this is equal to the power that you have to take a to in order to equal x. Well, if I take a to that power, I'm going to get x as a result. Okay? You have to think about that one a little bit. And this one here, if the log base a of x is equal to the log base a of y, what do you think would have to be true? Hopefully you said that x would have to equal y. So you'll see these properties again on page 189 of your text. We'll resume the second video here with these problems.